All right, everyone, we are on topic 4, student activity sheet 3, and this is the exploring direct variation. Okay, so what we're going to do is we're going to take what we know about this constant rate of change that we learned in the last student activity sheet and then apply it forward. So we have Josh, who works for a design company. He has to inspect 420 pairs of jeans today. Of the 84 genes that he has already inspected so far, 3 of them have had defects. So they want to know how we can find how many total genes Josh is going to find today if the defect rate remains constant. Okay. So in order to do this, we're going to do a couple of things here. What I want to do first is I want to talk about what we know. We know that if Josh, of the 84 that he has inspected, 3 are defective. Okay, so what I want us to do is I want to take this and kind of simplify this out. Okay, can I reduce that? And the answer is yes. 3 goes into 3 one time, and 3 goes into 84 28 times. Okay, so what happens there, guys, is we're going to say, all right, well, what times 28 gives us 168? And that would be 6. So I said, again, guys, what times the 28 genes? Because for every 28 genes right here, every 28, I find one defective pair. So how many sets of 28 are there? 6. How many sets of 28 are there in 224? And that would be 8. How many sets are there in 336? That would be 12. And there's 15 sets in 420. So again, guys, I said 28 times the number 3 gave me 84. 28 times what gave me 168, and that was the 6. So again, 28 times 3, and that's how I got 3. 28 times 6 gives me 168. 28 times 8 gave me 224. 28 times 12 gave me the 336. And 28 times 15 gives me 420. Okay, and I got that all from going back to my original of 3 over 84 simplified down to 1 over 28, meaning for every 28 pairs of genes I inspect, I will find one defective pair. Okay, if you want to take a minute and fill that in on your Agile Minds or your chart, you can. Again, I said 6, 8, 12, and 15. Okay. And then what they asked us to do here, guys, is they asked us to find the constant rate of change. Well, we did that when I said my original amount was 3 over 84. What I did is I simplified that. I said, can 3 go into 84? And the answer is yes, 3 does go into 84. So I divided both the top and the bottom by 3 to get my 128, 1 over 28. And all that means, guys, is that for every 28 pairs of genes, Josh should expect to find 1 pair of defective genes. Okay, so let's go on. Sometimes it takes a while for us to load this. Okay, so again, that's just going through the same exact thing that I just showed you guys. Let's go on to page 3. Or question 3. Okay, so now they want us to look at something else. For each row in the table, they want us to look at the number of pairs of defective genes, the number inspected. And what do we notice? Okay, so again, let's look at this table here. Okay, 3 over 84 simplified to 1 over 28. 6 over 168 simplified. Simplified, simplified, simplified. Okay? What I notice here, guys, is that the pairs of defective genes divided by the pairs of checked genes. So the total number that I look at on the bottom and the ones that I find that are defective, the zipper doesn't work, there's a hole in them. Okay? Every time that's simplified down to 1 over 28. Each one of these simplified down to 1 over 28. Okay, so now let's look at question 4. Okay, they want to know why we say the number of pairs of defective genes is proportional to the number of pairs of genes checked. Well, the first thing, guys, we need to know what the word proportional means. Okay, what does proportional mean? Proportional means it's a statement of equivalent, meaning all that means here, guys, is that 3 over 84 equaled the 1 over 28, and it works every single time in this problem, okay? And what happened here was that each time we compared the number of effective genes to the number of checked genes and simplified, maybe mark that down, and simplified or reduced and simplified / reduced, they were equal every single time, guys. If you look over here, every single time we compared the defects with the number checked, every time it reduced to 1 over 28. Let's go to number 5. Okay, so for number 5 here, they want to know what in the world is a constant proportionality. What is the constant proportionality for this situation? Well, the first thing, guys, that we need to know about the constant of proportionality is what it actually means. And the big thing with this is a constant proportionality is the same as the constant rate of change of a linear function that models the proportional data. Guys, all that fancy smancy words, the only thing that means is that what is the change that stays the same over and over and over again? What is the change? And that is 1 over 28. Okay? My constant of proportionality is 1 over 28. That's what each one of these simplified down to, is 1 over 28. Question 6. They want us to create several proportions with this. Guys, a proportion, going back to what we said on the other side, a proportion, maybe you guys remember this from middle school. Maybe it's like when we say 1 inch equals 3 miles on my paper, like on a graph. 1 inch on the graph is equivalent to 3 miles in real life. So if I measure something that's 2 inches, it's really going to be 6 miles on the graph. Okay, this is an example of a proportion. And really, guys, all it means, again, a fancy way of saying the fraction can be reduced. Okay, so they want us to create some proportions here. And I don't like what I have on my paper, so I'm going to put this here and we're going to write over it. Okay, looking at these, guys, I told you this is an example of a proportion. So what can I write here? I could say 3 over 84 equals 6 over 168. I could write 8 over 224 equals 12 over 336. I could write 3 over 84 equals 15 over 420. We could write that any one of these is equal to the other because they are. What happens is that they all reduce down to 1 over 28, So they all equal 1 over 28. Okay, again, something to note. They are all equivalent because they all can simplify down to this 1 over 28. Let's go on. Okay, so question 7 now. They want to know how many pairs of defective genes can Josh expect to find if he checks 112 pairs of genes? If they check 112, they want us, they want us to create a proportion to answer the question. Whoa. Let D represent the number of defective pairs. Okay, so what we're going to do here is we're first going to set up the proportion. Okay, we know that there is a 1 over 28, and that is going to be equivalent to something over 112 because he's checking a total of 112 pairs. D goes here for defective. We don't know how many. So what we're going to do is we're going to crisscross. Okay, 1 times 12 equals 28 times D. Multiply this direction. Multiply this direction. 1 times 112 equals 28 times D. Simplify that. That equals 112 is equal to 28D. We need to solve. Remember, guys, here's stinky. Get the D by itself. How do I do that? We're going to, this is multiply, so we do the opposite, and we're going to divide each of those by 28. And we find that when we do that math, 112, hold on here, 112 divided by 28 equals 4. If he does this, okay, if he inspects 112 pairs of genes, he will find 4 defective pairs. Okay, let's go on to number 8. So they have this equation, okay? They want to know what equation represents the statement y is proportional to x, and that is what we call direct variation, okay? That equation is going to, we have 2 of them that mean the exact same thing. We could either say y divided by x equals our k, our constant, or I could say equals the proportion, or we could say that y equals k times x. These are the same thing. Okay, what are the y and the x? This is from our table. This is from the table, the y value of the table, the x value in the table. Okay, our k stands for the constant or the constant of variation. This was like that is our 1 over 28 in this problem. Okay, either of these will work. We want to use the one, if we're having to find k, you're going to want to use this one. If you have to find y, you want this one. All right, so what in the world is direct variation? Okay, direct variation is when y varies directly as x. The change in y is a direct relationship to the change of x. The change in y is a direct relationship to the change in x. Okay? Turn the page. So here, guys, what they want us to do on number 10, they want us to graph the data. So I went, and now you're going to have to estimate a little bit. The first thing you need to do is know if this is 100, what do each of these marks stand for? Well, it's 20, 40, 60, 80, 100. Now it's 84 pairs of genes, guys. And I know genes go right here because it says pairs of genes checked. If 84 pairs of genes are checked, that's about here. This isn't going to be perfect. There's 3 defects, so I went and put a dot on 3. 168 found me 6 defects. 224 found me 8 defects. 336 found me 12 defects. And 420 found me 15 defects. Okay, So let's talk about some of the things that we maybe noticed with this graph. One of the first things I noticed is that this whole thing pretty much forms a straight line. Okay. It forms a straight line. Now, maybe your dots are off a little because we had to estimate points, but it's a straight line, guys. So it's linear. It is a straight line. I like to use the word linear. That's a proper way. Okay. Mrs. Stanton's way, straight line. The real way we say it, if you're a Mr. Case, Mr. Sears-Patowski, Miss Latimer, Miss Graham, use the word linear. Okay. They'll like you better for it. All right. Going on. This graph is increasing from left to right. That's another thing I noticed. As my pairs of genes are checked, my number of defects increases. As the number of pairs checked increases, my number of defects. Again, Mrs. Stanton's way of saying the more genes we check, the more defects we find. Okay, guys, that's what's really happening there. Okay. Again, what I want you guys to note, the last thing here, if we connect all of these points and extend that line, I notice it goes through this spot right here. Okay. That spot is what we call the origin, and it's at the point of 0, 0. What does that point mean? That means 0 genes are checked. And if 0 genes are checked, that means there's 0 defects found. No genes checked equals no defects found. Okay. Let's go on. Okay. So this is just saying exactly what we just said about things we notice with the graph. Okay. And then lastly here, maybe not. Okay. On number 11 here, they want us to look at the baseball cap situation. Now, we had this on the last activity sheet. Okay. We want to know if the amount of caps is proportional. Now, here's the thing, guys, what you need to recall. Remember, we said if it's proportional, that we're going to look at the y value divided by the x value, and that will give me my constant. We need to see if this is the same for each one. Okay, so when first thing, guys, when we have a 0, don't count that one. Okay, so let's look at my first bit of information. Okay, we had 10 over 1, $10 collected for 1 hat, then $30 collected for 3 hats, $50 collected for 5, 60 for 6, and 90 for 9. I can notice something right away about this. Hopefully you spotted it too. And that each of these reduces to 10 over 1. Guys, that means that $10 for 1 cap. We collected $10 for every single cap. Something else I noticed is that each of them can reduce to that. They are all equal. Because they are all equal, we are going to say that the ratio is constant. It's the same. It's proportional. Our amount collected varied directly with the number of caps sold. So now I want to go down and look at this table down here. We want to know if the data in this table is proportional. So we're going to look at each of these. We're going to say, again, be careful how we do this. Okay. The Y goes on top. Okay. Y always goes on top. If you got to star that, put it in your notes, Y goes on top. Okay. So we're going to say 5 over 1, 6 over 2, 7 over 3, and 8 over 4. And let's check it. 5 over 1 becomes a 5. 6 over 2 becomes 3 over 1. 7 over 3, that can't reduce. And 8 over 4 reduces to 2 over 1. None of these are equal to one another, which means that no, they are not proportional. Okay? Each ratio is not equal. Each ratio is not equal. Okay, let's look at number 13. Okay, so they want to know if we check 252 pairs, how many defects are we going to find? Okay, so this is question 13. If we check 252 pairs, what are we going to find? Well, the first thing, guys, let's talk about our equation. I said y equals k times x. Remember, x stands for the pairs checked. Y stands for the pairs with defects. So this y are the number of defects. Well, we just said how many defects. We don't know. This is our y, and it's unknown. Okay, if we are checking 252 pairs, okay, pairs checked, that's our x value. X equals 252. Okay, we know what k is. Remember, k stands for our proportion, and we've already said over and over again on this problem that our constant is going to be 1 over 28. So let's fill it into the formula. Y, our unknown, equals 1 over 28 times my x, 252. Simplify this. That's 252 over 28, which equals 9. If I check 252 pairs of jeans, we are going to find 9 defective pairs. This time, for number 14, we're going to go the other way. This time they say, how many defective pairs will we find if we check X? Well, we're still wondering for Y. We don't know, and we don't know X. So we're just going to fill in our blank problem. We don't know Y. We know our constant, and they're saying that X is X. This is the formula we get. Y equals 1 over 28 times X. Okay? And then last question here. Okay? This time, they say there's 30 defective pairs. 30 defective. Remember, defective stands for Y. Okay, again, that's on our table here. Our defects are Y, checked is X. How many pairs of jeans do we need to check? We don't know yet. Okay, so when I have my formula, Y equals K times X. Y is 30. K is our constant that we know. X is the unknown. Okay, Y equals 30. K equals 1 over 28. X is unknown this time. So now when I plug this into the formula, we have that 30 equals 1 over 28 times X. To get rid of that number in the denominator, we're going to multiply by 28 on both sides. And when I do that, my 28s cancel here, and I'm left with X equals 840 jeans checked. Okay? And that is it for student activity sheet 3.